Log on, tune in, find out. Another good idea from Cambridge.
The next speaker in the morning session is Thierry Paul from École Polytechnique, and Thierry is going to speak to us on quantum mechanics with a singular classical limit.
Thank you, Peter. Is it okay? Can anybody can hear me? Yes, it's on. Cannot. Are you hearing me in the back? Yes? No? Apparently not. Yes? Okay. Okay. So, thank you, Peter. I want to apologize because I changed the title and the contents of my talk today. I found by preparing the last topic that it was maybe a little bit technical for diverse audience, and so I will speak about quantum mechanics with singular classical limit, and it might be somehow related also to some ideas expressed by Xi in the last talk. So let me start by some general remarks about what we call semiclassical limits, in which some people don't like the word because the Planck constant has to be a constant and blah blah blah. So let me remind you that most of the times what plays the role of a Planck constant in a Schrödinger equation is in fact a combination of several things, and the true Planck constant might remain fixed, although you're just looking at part of the spectra of the objects you're looking at, which look like semi-classical. For example, if you take just a hydrogen atom, you have some scaling phenomena which tells you that looking at fixed value of h bar and looking at the high part of the discrete spectrum is equivalent of looking at the low part of the discrete spectrum and let h bar tending to 0. So this is for this kind of equivalence because between high part of spectra and semi-classical limits. And let me give you another argument coming from experimental physics, saying that nowadays it's really a regime that people achieve very easily. For example, in the Laboratoire Kastler-Brossel in École Normale, you can perform experiments with atoms of rubidium where you excite an external electron in such a way that it's do you mind if I switch this off? Because can I switch it off or not? Because it's kind of noisy. And when you when you put the external electron in such a high level that in fact the wave function has a support, that is the volume, basically to speak in classical terms, the atoms occupies a volume which is of the order of a small bacteria. That is, one atom have a volume of around the micrometer. So this means that you are really attending such high level of excitement that in fact you have some kind of almost macroscopic scale of space which enters the game. So you are truly in a kind of semi-classical limit. And also if you think about time, you also reach scales of time which are of the order of the minute. I mean, they are able to perform this excitement of the electron, external electron, and keep the atoms in this state for time scale of the order of the minute. So this kind of dichotomy between, you know, short time, small space for quantum, and long time and large space for classical is in a certain sense experimentally in question nowadays. Okay, so a main difference between, of course, quantum mechanics and classical mechanics, probably everybody knows that, is the fact that the second one is local, the first one is not. And the incidence of this fact about Hamiltonians is the fact that you need very, very low regularity. For example, you have a Schrödinger operator, you need very low regularity on the potential in order for the dynamic to exist. You have a Kato condition. What you need really is the fact that the Schrödinger operator is essentially self-adjoint. And of course, this has nothing to do with the regularity you need at the classical level for the underlying Hamiltonian flow to be well defined and the equation to be well posed. So my subject today will be to try to understand the link between these two extreme cases where you have on one side a very well posed Hamiltonian flow, and on the other side a quantum dynamic with a unitary evolution operator which is ensured by very, very low regularity. Now you might think that this is just a mathematical problem. Why should be interesting to consider rough potentials and underlying singular classical dynamics? Well, the first example is given by Xi in the preceding talks, that is in Born-Oppenheimer approximation theory. You get easily, when you have this crossing phenomena, I don't want to repeat them, get easily to potentials which might be very singular, at least to be less than what is needed for the classical flow to be well defined. There are a lot of other situations. For example, situation where you have system with symmetries, and of course you, in order either to compute, either to get information about the quantum evolution, you try to reduce the symmetry by quotient by the symmetry, and then of course this quotient might be nice, and sometimes they are not nice, and this leads exactly to a singular potential or singular Hamiltonians. A very simple example of this is when you have two-dimensional harmonic oscillators. The general fact is when you have basically a degenerate eigenvalue and you want to perform perturbation theory and you want to perturb a degenerate eigenvalue, we all know that what you have to do in this case is to diagonalize the projection of the perturbation, the eigenspace, and if you perform at the same time perturbation theory and semiclassical approximation, this means that in general the degeneracy will increase when h bar goes to 0, and the projection of the perturbation will become semiclassical operator, in fact. And semiclassical operator with fake Planck constant, which is going to be the dimension, the inverse of the dimension of the eigenspace. And what you get in this case is a true semiclassical theory for this part, but in some cases you have very singular symbols of your Hamiltonian, of your reduced Hamiltonian, so to speak. Just think about a two-dimensional harmonic oscillator. When the two frequencies are not equal and rationally dependent, is exactly what you get. So a lot of situations where you get singular Hamiltonians. Okay, it works. So I will be. Yeah. So the general setting will be the Schrödinger equation, posed like this. When you have I h bar d dt psi is minus a bar squared Laplacian plus v acting on psi with an L2 normalized initial condition. I'm going to play like in LaTeX. I will make immediately a new comment. H bar is going to become epsilon in most of the slides today, and this is just a way of facing applied math with mathematical physics. Now we all know that this equation, if we take, if you think about it with orthonormal projection is on the initial datum psi, is equivalent, and equivalent only in this case, to this equation, which is called von Neumann-Heisenberg equation, which tells you that the derivative of the matrix, the density matrix, is 1 over I h bar times the commutator of h with d, where h is a Hamiltonian here. And generally you impose to d this kind of preserved properties, that is, it's positive and the trace is equal to 1. Now the game consists in letting h bar goes to 0, and we all have seen that associated to this kind of quantum Hamiltonian is associated a Hamiltonian, classical Hamiltonian, p squared plus v of x, and the general rule I'm going to comment more precisely later on is the fact that 1 over I h bar, the commutator, should tend to the Poisson bracket in the setting of classical dynamics. This remark was first done by Dirac in Oxford, sorry for that, but and the starting point of all the semiclassical approximation, a way of looking at it. Okay, so In some cases, you have very nice convergence of the equation, but you need a lot of regularity in order that this simple convergence of equation leads to convergence of the solution. And also, as I mentioned before, the regularity needed for this to be a very good generator of a quantum flow is the conditions are very weak compared to what you need here to have well-pointedness of Liouville, or even worse, to Hamiltonian flow. So this will be my discussion. More philosophically, I would say that what you're looking here with this kind of limit when the potential is not very regular is a true inspection of the underlying space, the space of classical mechanics, which is the space of the variable of the wave function in quantum mechanics, and which can itself becomes singular. If you think about the example I was mentioning of the 2D harmonic oscillator, what you get by taking the quotient on a degenerate eigenvalue is either a regular space with a singular Hamiltonian, or a kind of with quotation mark regular Hamiltonian on a singular space. Okay, so what are the issues? So first issue was nonlinear, but I'm not going to talk about that today. One issue that you can very easily check and look at the funny part of it is when you take a complex potential. So of course when you take a complex potential, you're out of the general condition for having a nice unitary quantum evolution. But still the equation is very well posed because the equation lives in the complex by itself. So if you think at the equation at the beginning, this one here, if V now is a complex, at least the equation exists. And if you think that instead of having, for example, this L2 condition, I mean this L2 setting for the Hilbert space, if you think that the Hilbert space here should be, for example, finite dimensional, which is a situation which arrives in quantum mechanics, then there is no problem by handling this equation. At the contrary, of course, if you look at an equation, Hamilton equation, with Hamiltonian p squared plus v of x when v is complex, you immediately take off from real space. So this means that the underlying equation is not well defined. So it's a topic I'm not going to talk about today, but it's easy to get convinced that complex potential in the classical limit is also an interesting fact, and you see exactly that you get in the limit some kind of non-classical equation, because a naive classical equation would be complex. So the main issue here today will be regularity of V, and regularity of V means that from Kato condition, which I will remind later on, but it's not, I don't want to spend time on this, to C11 condition for the potential, that is a Lipschitz condition for derivative, which is a natural setting for having a well-posed classical equation, thanks to the Cauchy-Lipschitz theorem. So you have several examples. For example, if you take an Hamiltonian of this form, at least locally near the origin, when theta between 0 and 1, you get immediately out of this condition C11, although the quantum dynamics once again is well defined. And at the end of the talk, I will talk about this precise example and show you that in the classical limit, coming from a quantum evolution with this potential here, you will capture all the features of this not well posed classical evolution. Okay, so to concentrate or not to concentrate. Okay, so one of the main hypotheses I will have on the potential here will be that its gradient in BV. It's not the same V here and here, of course. And for this, in kind of this condition for the potential, of course the quantum flow exists, absolutely no problem, and the classical flow exists too in a kind of normalized way. It's thanks to the theory of Di-Pern-Alliance and Ambrosio. And in this case, the result, which I will be, of course, make more precise, will be that the Di-Bernalian-Ambrosio flow, this flow which is defined almost everywhere with a kind of regularity property, will be exactly the classical limit of the quantum flow. But this will be only for non-concentrating initial data. Not concentrating initial data, I will, Wigner function has been defined in the preceding talk already, so I will set up in the Heisenberg equation. So I will have Wigner function of the density matrix, and the result, the general result in the case of BV vector field will be that, in fact, your Wigner function cannot concentrate near one point, which is in a certain sense coherent with the fact that the underlying classical flow is not defined everywhere. But still, it's kind of a problem, and you would like to have concentrating initial data. So if you want to start by concentrating initial data, so concentrating dynamic in the ing of concentrating means when the Planck constant goes to 0. For that, and I will need a little bit more regularity than this, but still I will present some result where the regularity is not enough to ensure uniqueness of the flow everywhere. And in this case, I will show you that when you take a Wigner function which concentrates at a bad point of the flow, that is a point where, for example, you have two bicharacteristics for starting at the same point, the classical limit of the Wigner function will capture the two of them, and I will discuss that. So it will be, in a certain sense, a way of defining, so to speak, everywhere an evolution for a flow which is defined almost everywhere, but by losing the classical paradigm telling you that if you start by one material point, you always have a flow. You will have just creation of two material points out of one. Once again, this will become, I hope, clear. Now, if you think that the general Kato condition, or even worse than Kato, if you just would impose that your potential just leads to a self-adjoint quantum Hamiltonian, is totally open, and I think it's something which would be very nice to have some general information about the classical limit for very, very rough potentials. Okay, so Wigner and or Ushimi. So let me start by Wigner again, although it has been introduced in the talk before. So, oh, there is a mistake here. Hermann Weyl was not living in the Middle Age, but this is 1928 here. Actually, this date here is about the date where the musical notation was invented. You know, musical notation with bars and notes comes from the year 1000. It's very stable because it's still used. So it's kind of example. So the Wigner function, the starting of studying Wigner function doesn't go back to Gerard, Paul, Markovitch, and other people like this, but it has been done by Hermann Weyl, and I advise everybody to have a look on the book by Hermann Weyl about the title is Group Theory and Quantum Mechanics, where the Weyl calculus is defined. And then it was totally forgotten, not for 1,000 years, but for at least 30 years, till the pseudo-differential calculus was reborn in the late 50s by Calderon and Zygmunt. A few years after, Wigner defined his so-called Wigner function, and the link between the two is the fact that the Wigner function of a function psi is nothing but the Weyl symbol of the projector on psi divided by epsilon or h bar to the n. So it's just a rescaling of the Weyl symbol of the projector. So Weyl calculus deals with operator, Wigner function deals quadratically with function, and the link between the two is this one. Let me mention that also it was discovered by Will in the 1940s and late 40s in signal analysis, then quotation mark, and then you have this series of paper, and then quotation marks are a lot of other things, including the work by Gerard Fermanian that were mentioned a little bit before. So the definition, taking psi in L2, the definition of the Wigner function is given by this formula here. That is, you take the Fourier transform of the two-point correlation, basically. And once again, for people who knows what the Weil symbol of an operator is, you can check that this is true. And for people who doesn't know what the Weil symbol of an operator, you can check that this is, in fact, the symbol of an operator. Under some tightness condition that I domained here, compactness methods tell you that the Wigner function tends weakly in some space, which I will define in the next slide, sorry. Well, I mean, if I tends to a positive measure of mass, which is the norm of the original function. I will also come back to this later on. And in fact, you might wonder why the limit is positive, because it's very easy to check that this function here is not positive as a function of x and p in general. It's positive for a Gaussian, it's positive for class of function, but it's not always positive for any psi. And the reason for that is that, in fact, if you just modify the Wigner function, that if you smooth by a heat equation at time epsilon, so epsilon enters here in the definition of the Wigner, then you get something which is positive. And of course, by having this smoothing, this modifying of this, the limit will be the same. I'm a little bit fast on this. This means that the limit will be positive. And why, in fact, this condition is positive? It's very easy to see that this condition is positive because it's a square modulus of complex number, which is a good reason of being positive. And it's a square modulus of the scalar product of the original psi with a set of so-called coherent states. So I'm not not important to know what they are here, but it's just the fact that it's an L2 function. So this ensures that this is positive. So it will be two of the main ingredients for the discussion later on. That is, Wigner function is very nice. It has a positive measure, but it's not positive. And sometimes it's easier to work with a kind of modified version of it, which makes it positive, just to get some kind of estimates. I mean, in mathematics, one likes positivity usually. And the second part, the second things about this formula, it's the fact that it gives you an L infinity bound with respect to the L2 norm of psi, which is the fact that the L infinite norm of the Houchimi function, so this is the Houchimi function, is bounded by epsilon to the minus n times the norm of L2. So the bound blows up when epsilon goes to 0. Of course, it's only a bound, but I think it's an open question to know if this bound is sharp, or at least if it is possible to find sequences of function in L2 with, for example, bounded L infinity bounded Houchimi functions. I don't know the answer of that. I try to construct example. It always fails, and it is crucial for what will follow now. Okay. So if somebody has the answer of these things, we'll be happy to have it. So two ways of looking at phase space distribution, Wigner and Houchimi. So that's the moral of the talk. Okay, so what about now a little bit of dynamics? So once again, I showed you that under some mild condition, the Wigner function has a limit after extraction of the subsequence. I mean, all this machinery of compactness method enters again here. And now what's about the dynamics? Well, if I write the dynamics once again as, instead of taking the Schrödinger equation, writing that the derivative of the projector, orthogonal projector on psi, is a commutator divided by h bar of the Hamiltonian with itself. And if I take these rules, which can be easily at a formal level derived, we get that the limit of the Wigner function should satisfy the Liouville equation. I'm a little bit rash on this, but it's something easy. For people who wants to check this, it's very easy to check these rules just by taking a differential operator with polynomial constant. We just plug this on the commutator. You compute, you use the commutation relation between the operator of multiplication by the variable and the differential operator, and you get immediately that this is true here. So you get that hopefully the limit equation for the Wigner function, that is for the limit of the Wigner function, which will be a measure, Wigner measure, should be Liouville. So when is it true, in fact? Well, it's true, it has been proven that this is true if the potential is C2. In this case, you have unicity of Liouville, of course, and then you prove that the Wigner function converges to the solution of Liouville. There is only one, because the flow is very well posed. So you might ask, well, but in fact, C2 is a too strong condition on V for the classical flow to be well posed. It could be lower, for example, C11. In this case, I don't remember if this is true or not, but let's just look. Let's just look directly to just a C1 condition of V. In this case, the classical flow is not all the time well defined, all the time in the dynamics inside the dynamical system. And in this case, what we proved in the old paper, is the fact that the Wigner function will converge to a solution of Liouville. You know that after extraction of subsequence, you get a solution of Liouville. There is no clue of knowing which one you will have in case the Liouville equation has two solutions or more than solutions. So about this general panorama, what I want to say is that one goal in order to try to improve is, of course, to lower the regularity of V, to understand in which sense you will converge to a solution, for example, in case where you have two solutions, which one you will capture, and to have a precise convergence limit. Get rid of the subsequence, which is obtained because you're using compacity methods. And also a last part, which will be the last part of my talk, to get maybe not only convergence, weak convergence limit, but also to have strong convergence limit in space, for example, L2, which is a preserved norm for the Wigner function. And to have strong convergence with precise estimates of the remainder, because it happens most of the time that the semi-classical approximation is very good, it's very efficient, and for that, of course, you need to precise estimate the remainders. So not only semi-classical limit, which per se is a strange word, we should talk about just classical limit, but semi-classical approximation with estimation of the remainders. Okay, so weak first, strong then, weak and strong, because I'm going to try to show you that sometimes if you have some strong information, it's unfair on the weak limit and precise some results. And I will, at the last part, go back to the potential I was mentioning, with the potential minus absolute value of x to the 1 plus theta, to show you how you can get splitting of wave packets when you arrive at the scatter. Okay, very briefly, and in fact I'm starting to be late. Dependent-Lyons-Ambrosio theory. What does it tell you? It tells you that at a classical level, this is purely classical, that if the gradient of your potential is locally in BV, and this kind of condition for the essential lead supremum, I'm not saying that this is the sharpest condition, but it's enough for what I need. This implies that if you take the Liouville equation with an initial condition which is in L1 enter L infinity and which is non-negative, you have existence and in uniqueness in this space through a non-negative solution, distributional solution of this equation. So I don't want to enter too much in the details, but the crucial thing is that you need to start by something which is in L1, enter L infinity, and non-negative. So if you want to compare this to what you have in quantum mechanics, where W0 will be replaced now by either the Wigner transform, either the Houchimi transform, you will get trouble, except this condition, even this condition actually, will get trouble with this, and you will have to do something in order to see that the limit equation is well posed in this kind of situation. So so the problems which arise that first of all you need positivity and you need L infinity. So if you remember, I told you that the Wigner function is not positive, and you can replace by Hushimi function, which is positive, but Hushimi function is not in L infinity. So you have to a little bit play with these two because none of the things are satisfied by a single object, so to speak. So nevertheless, the solution is that, of course, to get positivity, you will work with Hushimi function, that is, once again, modifying Wigner function in such a way that it makes it positive instead of the Wigner function. And in order to get L infinity, there is nothing to do because I don't know. Even I think if you would construct an initial datum which is in L infinity, this condition wouldn't be preserved, so you will get in trouble. But in fact, instead of taking a single initial datum, the idea there is to average about a family of initial data. But as you see, in a certain sense, there is something kind of iteration. You know, it's play it again, Sam, it's a game in such a way that is, you know, that the classical flow is not well defined everywhere, but on average, that is in measure sense, you can define the flow. Now you have another problem now, which mimics this one, is the fact that the flow won't be defined for any initial condition, but if you smeared by a probability density on the initial datum, you will get something and play again. Once again, you will, in fact, what you will do, you know, the heart of the theory of Di Perna and Lyons and Broglie is to replace an ODE by a PDE, and then you will consider that the PDE, the Liouville PDE itself is an infinite dimensional ODE, and you will replace it by a PDE, an infinite dimensional PDE. So it seems a little bit complicated. It is, in fact, you have to, basically what you have to do is a Di Perna Lyons and Broglie theory for flow on space of measure, because you're taking average of your initial condition. But it works, and what you get is the following. If you put some kind of assumption on V, so you want V to be globally bounded, locally Lipschitz, sorry, it should be a V here, it should be in BV log, and also this essential, I mean, I don't know if it's an essential condition, but it's a condition, is the essential spectrum supremum of this quotient here. In fact, I put it was a mistake to put a UB instead of V, because in addition to this, you can add a finite number of Coulomb singularities, which are treated by another method. But the potential should be a finite number of Coulomb singularity plus a potential V, which will satisfy these four conditions. So these are the assumptions on the potential. What are now the assumptions in the initial datum? Well, you will need a family of initial datum. So epsilon is a Planck constant, 0 is the time, this is the initial datum, and W will be a parameter which will index the smearing you are going to do. That is a probability variable, so to speak, a random variable. So we need that this is in H2, and this kind of condition, this is a boundness condition with respect to the Hamiltonian you're looking at. So once again, you take basically something like the average of H squared into the initial datum, and you integrate over the random variable in order to have something which needs to be finite. The most important fact is that what you need is that this sum here as an operator, once again, this is the orthogonal projector on this, so you take the smearing of the orthogonal projection on the initial datum, and this has to be a small operator of norm epsilon to the n. I will go back on this later, but this is a condition. Of course, you know, once again, this is exactly, you mimic the fact that you wanted this to be bounded. It cannot be because of the bad bound I showed before. So you need this again. Then you will have a flow almost everywhere for with respect to the parameter W. I will work with this kind of norm, which is now a classical standard norm, so to speak, in this kind of things. The space test function will be space of function phi, which is bounded with respect to this norm. And what you get is the following. So this is a result by Luigi Ambrosio, Alessio Figali, Gero Friseke, Johannes Giannoulis, and myself. I put it in a kind of fancy way, but in fact I will not spend so much time. I will go to the second result, which will be more simple in a certain sense. So in order to show the convergence you express in terms of a distance, and if you're working with Hushimi, you have just a distance inducing the weak topology in the probability measure. Otherwise, you have a distance for Wigner, which is in the weak topology in the dual space of the space of test function that's just defined. Sorry? Kubi-Wasserstein. And what you get is that you get a flow here. That is, you will have that this, let me take this on Hushimi, for example, which be close to this flow here after averaging above the parameter, and when you take the limit uniformly in time on the final, locally uniformly in time. So let me just I don't want to enter too much details, but what is this mu of t? It's a flow, and it's a regular Lagrangian flow, and compared to regular Lagrangian flow on probability measure that we have usually in this set of generalized solution for ODEs, you will have in this term a regular Lagrangian flow on a probability space on probability itself because of this averaging here. So let me go to the next one, which will be maybe easier to handle. This is a little complicated in somehow, but you see, basically, let me give the argument which made you. What you look in the preceding formula is an object like this, which means that you have a kind of integration with respect to your probability space of this distance. Of course, if this is bounded now. And if you enter this inside, you can play this little game here. And at the end, what you end up is the fact that you get just the average of a smearing of projector on your initial datum or even evaluated datum. So now this, of course, is a sum of projectors, so it's not anymore a projector, but it's against a positive trace 1 operator, that is, it's a density matrix. So the idea would be to pass from this formulation into another formulation which will be simpler, but will not consist in averaging initial datum inside the Schrödinger picture, but taking density matrices. So this is what we did in the next result. So now you don't speak about Schrödinger equation, take directly the Heisenberg von Neumann equation, and you take an initial datum, which is a density matrix that is positive and of trace 1. Do you have the same assumption on the potential? You also can, didn't mention here, other Coulomb singularities. You have basically something which mimic the assumption on initial datum you had, that is, you suppose that the trace of H2 times initial datum is bounded, that the density matrix, although it's of trace 1, as an operator, it's bounded by epsilon to the n. So this means that, once again, it's a trace in the sense of, is the fact that your initial datum has to be spread around, because all the eigenvalues have to be bounded by epsilon n, but the sum has to be equal to 1. So this means that you have something which spread on its own spectrum, so to speak. And once again, you have the fact that you have a weak limit of the initial datum, which is not really an hypothesis. It can be implied by tightness condition once again. And what you get, once again, we take these two limits, and this is a theorem by Alessio Figali, Marilena Ligabo, and myself, which in this case, you have exactly the fact that your evolved Hushimi of Wigner is close to a classical one with respect to this topology, and W0T, 0 for epsilon is equal to 0 and T for the evolution, is a unique solution in this space of the Liouville equation. Once again, done by the Diperne-Alliance-Ambrosio theory. So what you see is that basically the machinery works, the usual machinery works, so to speak, of semiclassical, that is, you have Wigner functions. They tend to a kind of object which is evolved by a Liouville equation, but once again, you need this non-concentration fact drastically. I mean, this is very drastic in the sense that you have absolutely that you basically, when you express your density matrix at time t equals 0 on its spectrum, it has to occupy a volume of order 1 over epsilon minus n. So it has to be really very, very spread. Okay, so let me, I think, yeah, give some example of initial datum satisfying the required assumptions here. Well, the first example is when you give yourself the initial datum directly as a sum of projector, for example, on a set of Hermite functions, semiclassical Hermite function, that is, you take the usual Hermite functions, product of a Hermite polynomial by a Gaussian, and you rescale it by square root of epsilon, 1 over square root of epsilon. And then it's very easy to see that the condition of the theorem are satisfied. You have this condition, boundness of this by epsilon. I did it in one dimension. So once again, this is a trace of the fact that the norm of the operator has to be small. And these two conditions, this one is just condition size, and the other condition is more subtle. It tells you that when you distribute the mu j and you take this measure on the phase space, this has to tend to a measure in the probability of R2, because n is equal to 1. And of course here, for people who know, you recognize exactly here the Wigner measure of a projector of an Hermite function. Okay, so this is the first example. The second example comes from Toplik's quantization. In this case, instead of expanding your initial condition on a discrete, on an orthonormal basis, you're expanding into a space of so-called coherent states. You see this vector here is what? This is basically a Gaussian, or in fact any other nice function, which is localized near Q at the scale square root of h bar, and which is modulated by exponential which oscillated like W over epsilon. So if you start by this kind of ansatz for initial condition, if you have those three conditions, that is, first of all, the key, the weight here has to be bounded in an infinity. It has to have a limit, and you have this size condition here. Then in this case, you satisfy the condition of the theorem. This gives you another family of initial data. You know, when you, something I didn't mention, but when you look at the semiclassical approximation with, once again, with rough potential, you need some kind of a strong condition on the initial datum, which is a fact which arises, for example, when you look at also nonlinear problems. In the old paper by Lens and myself, we show that if you want, for example, Poisson Schrödinger to tends to Vlasov, you need a kind of uniform L2 condition on the initial datum, which is not, for example, satisfied by a pure state. Okay, now if you just take no ansatz basically, but you take then the general density matrix, which has a Wigner function, the question is, can you impose some condition on the Wigner function so that you satisfy the hypothesis of the theorem? Well, then you need to be a certain kind of bound of the operator, of the density. Tremendous density operator has to be bounded by epsilon to the n, and this you can express into Calderon-Vaillancourt theorem, and it gives you a condition like this, and then the size, this trace of the square of the Hamiltonian to be bounded is reflected by this condition on Wigner. So you recognize here the beginning of the, this is just the Weil symbol, the leading Weil symbol of the square of your operator. What do you mean of wave function of pure state? Yeah. Oh, this is wrong. Because this will never done. Yeah. So you will have mixed state from the beginning. So give me a density matrix. I compute its Wigner function and I check if those conditions are satisfied. They are not sharp at all, but.
Okay, but you cannot sort of characterize it in terms of conditions directly on the density.
Yes, you can. No, you can, because this is just the fact that the density matrix is bounded by epsilon to the n in the operator norm. And this is the fact that the trace of h squared times the density matrix is bounded. But somehow it's not easy to check that. I mean, I don't know. It's just a matter of taste. But sometimes it's easier to, at least you would like to check it directly by the Wigner function.
Well, yeah, but it's important that you understand that you don't have a trivial condition. You have a sort of a condition that cannot be satisfied, right?
Oh yeah, no,
You
but
have to have,
but then you know those two examples are very concrete. So those two examples are true examples. But suppose that you don't know the ansatz of your density matrix, you just know the Wigner function, you just can check this one. And you see, usually in question of size, you just have usually, I mean, I'm talking maybe to specialists now, you have usually an integration of a symbol times the Wigner function. Here, because you need not the trace of h, but the trace of h2, and the trace of h2 times the density matrix is not expressed automatically on the principal symbols, because when you have two operators it works, when you have three operators it doesn't work. You get an equality which starts by here, you recognize here, of course, the square of the symbol of your Hamiltonian, but you get this extra term here, which comes from the fact that you have to go to the subsymbol, so to speak. And of course, you might say that this is questionable because V is just BV, but you have to interpret this by integration by part and by putting one derivative on the Wigner function. Okay, so those are three more or less concrete criteria for which you have this, and once again, this absolutely forbids to have concentrating initial data. So now I pass to the strong topology result. Why strong topology? I think I mentioned that already, and I'm short of time. So now I will have some more new and more stronger. Since the result is a strong topology, the hypotheses are stronger also. I will need a condition like this, plus a condition of this kind of things. I don't remember. Basically, I don't want to comment. It maybe could be expressed more synthetically, but everything is mimicked, of course, on this example in 1D, where you have Vx in minus x to the 1 plus theta, where theta is from 0 to 1. So the general hypotheses are this, but the motivation was this one. And now you define also a modified version of the potential, which is just the heat equation acting at time epsilon 2. This will be important for the result. Now you have some new assumption of W0, and the new assumption of W0 in this case are a little bit strange because you have first of all an H2 condition, that's fine, but the second hypothesis will have the following structure. You will look at the solution of a Liouville equation, you see, with, instead of V, you take the modification of V. So this means that V now is very regular potential, not uniformly in epsilon, of course, because V itself is not regular, but its modification is regular. So this equation with this initial condition, which is the limit, the initial condition at time t equals 0 of your equation, this, of course, rho is a very nice function, but not uniformly in epsilon. That's the point, because when epsilon goes to 0, the modification disappears here, and you get again a non-well-posed Liouville equation. So the hypothesis on the initial datum is the fact that the solution of this has to have this kind of H2 bound. That is, the H2 bound, the H2 norm of rho of t can blow up when epsilon goes to 0. It should be at one point because you recover kind of singular situation. But it has to blow up for some delta and for some negative power of epsilon. So you might say that it's a tricky condition because the hypothesis on the initial condition is reflected by the solution of an equation. But of course, in some cases, we can, I mean, in cases which are most interesting for us at least, you can check this. That is, you can check that indeed the solution of this satisfies this. But we couldn't perform a kind of synthetic condition telling you that this is going to work for general things. And in fact, it will be reflected by the result itself. So this is a theorem by Agis Athanasoulis and myself, which tells you that the true Wigner solution of our Schrödinger, Heisenberg equation, is close to the solution of the Liouville equation with modified potential, and is bounded by a power of epsilon. This k has an expression which is explicit. So you see, in this case, you don't look at the comparison between the true Wigner function and the true solution of the Liouville, which is bad anyway, but you compare the solution of the Heisenberg equation to the solution of a regularized Liouville equation, so to speak. And in this case, you see that the difference between the two in strong L2 topology is small, basically. So this is a little bit change of the game, and I'm going to show you what we can have from this, and this is our second theorem. And our second theorem, you need some extra hypotheses. I'm not going to comment all of them, basically, here. And the theorem is the following. Now, it's a weak topology result, and it tells you now that integrating against a test function, always in the same space of test function, of your solution is closed with a precise remainder estimates to ρ1 of t, where ρ1 of t is again the solution of this equation. And then you have a precise estimate of the remainder. So I really have to finish in 2 minutes, so I'm not going to insist on this, but it's just a change of point of view. Maybe it's a bad point because you need some extra information, but it seems at this stage for us at least it was necessary to impose this kind of condition. So let me go back now to our favorite potentials, minus x1 plus theta. So let us take in 1D this potential, and in fact we multiply by a beta of x, which is just a cutoff, that is beta of x is a function which is equal to 1 is 0, and then which tends to 0, in order to have some condition at infinity, which makes the potential the Hamiltonian quantum dynamics and quantum and classical dynamics works somehow. And it's very easy, if you want, you can perform the solution, the computation itself, that you have two solutions, x plus and minus p plus and minus, which are given by plus and minus c0 this, and plus and minus c0 nu t nu l, nu is equal to that, c0 is equal to that. Basically, if you start for your Hamiltonian flow at the origin, you have two solutions. In fact, you have three. You have one solution which stays at 0, solution which goes to the right, and solution which goes to the left, for me. It's typical example where you have degeneracy of B characteristics. So now what's happening if you consider that you take your Schrödinger equation, I mean the Heisenberg equation with this potential, and we take an initial datum which will concentrate at 0. You see, it's a shape function W which is fixed. You rescale it by lambda. Lambda is of log type behavior in epsilon. You have a certain power, blah, 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 whatever. You need the support of W, which is in the unit ball. And what you get is, in fact, that for finite time, you see, in fact, this bound over the time just depends on the cutoff you made. So you can basically extend to any time you want, but of course, you have to fix up about for the time before taking epsilon to 0. That is, Wt converge in weak sense, always in the same space, to two deltas reflecting the two solutions. That is, your Wigner function concentrate at time t equals 0 to the point to the origin. Then you let it evolve, it has this life, or her life, and then when you take epsilon goes to 0, it tends to superposition of the two points which has emerged from the singularity point. And the point is that now, of course, since this is a measure, you have here two measures, and you have here an addition, which reflects the fact that you can add measure, but you have also coefficients there, C plus and C minus. And those C plus and C minus reflect exactly, are given basically by some quantity reflected by the way you're concentrating near the original. So what I'm just saying is that you get a solution which captures the two solution of the classical flow, but nevertheless, you cannot speak about the self-contained flow because the ponderation between those two deltas are given by something which comes from the way you concentrate to zero. It's not something that you can see just on the limit. Well, perspective, stronger concentration towards per state, strong approximation by Smooth-Liouville for general dipernal ions, blah, blah, towards Kato class, because let me just finish by just a frame like this. So at the top you have Kato, telling that under this type of condition, you have the quantum dynamics. In fact, I should have put over Kato that you have just von Neumann condition, basically telling you that it's enough, stone condition more, telling you that it's enough that your Schrödinger operator is self-adjoint. If you go down to Wigner, already you lose a little bit, as people, specialists know, when you want to pass from Schrödinger to Wigner, in order that the dynamic exists, you lose a little bit of regularity. I mean, you need a little bit more of regularity. Then in order to go to Liouville, you need this condition, which is, of course, much, much stronger than the other one. And if you go to Newton, since we're in Newton Institute, you will have this kind of condition, which is much more than this one also, and you will have this kind of ubiquity phenomena. And, well, thanks for the end and for the whole session since I was here for today.
Thank you, Thierry. Comments, questions? I have a question actually. I mean, do you think that this work on singular potential sort of brings you closer to the pure state Schrödinger-Poisson classical limit? Which is something that we cannot do except in 1D, right?
Yeah. I don't know. The goal would be, you know, if you want absolutely to have pure states with rough potentials, you need to average this first part of my
yeah, exactly. I mean, the idea sort of could have some merits for the nonlinear problem.
Exactly. So you need to average. Now, if you want to have still and then you lose any kind of concentration.
Right.
If you want to have concentrating initial datum, what you have is to have to compare this to a basically smoothing of the Liouville. I think it should be, I mean, it's just as a picture, it should be a way of looking at, I mean, you know, concentrating at one point is it's like taking from an average of our initial datum to a single pure state. That we concentrate in a space of pure states, so to speak. And I'm working on that, but I have no idea up to now. But it should be, you know, since the first part we use everything you place into probability over probability. Concentration in space should become concentration on a pure state,
Right.
and maybe something would be possible to do.
Any more comments, remarks? Well, if not, then we thank Thierry.